the final method that we are going to cover in algebraic equation solving is the Newton-Raphson's method. Okay. So again we are interested in solving f of x equal to 0, and in the Newton-Raphson's method what we do is essentially we look at the curve. So this is what we did in the secant method is we had for example 2 points, and we connected those 2 points by a straight line, the point at which that particular straight line intersected the x axis is what our new guess essentially was. So this was our x I plus 1, or rather let us say this was our x2, okay. Then x2 and x1 we connected with a straight line again, and where x2 and x1 we connected with a straight line, and this became our x3. Then x3 and x2 we connected with a straight line, and this became our x4. So what happened in secant method is x2, x3, x4 when we started doing that, they started coming closer and closer to each other. So so let's consider the case where x2 and x3 are going to be very close to each other. So this particular line segment that joins x2 and x3 is nothing but a slope of the curve close to the point x3. So the question that we ask ourselves is, instead of calculating the slope of the curve by using the previous solution x2 and the current solution x3, what else can we do in order to get the slope of that curve? And the straightforward answer, what else we can do to get the slope of the curve, is nothing but its first differential with respect to x. So that is what we do essentially in the Newton-Raphson's method. So what happens in the Newton-Raphson's method is we do not start with two solutions, but just like fixed point iteration we will start with only one solution, okay. So let us say this sorry, not one solution, we start with one initial guess. This is our x1, we will obtain the tangent to the curve at point x1 and draw that particular line and find the point at which the tangent intersects the x axis. That particular point is our x2. At f of x2, again we find a tangent to that curve, find where it intersects the x axis, that becomes our x3, so on and so forth, okay. So the what we obtain is essentially we find the slope of the curve at xi. The slope of the curve of xi is nothing but f dash of xi, okay. So the slope of the curve is f dash of xi. The line that passes through that particular point with this particular slope is nothing but y minus f of xi is going to be equal to f dash of xi multiplied by x minus xi, okay. Again this is the slope, this is a line with slope f dash of xi that passes through the point f of xi comma xi comma f of xi, okay. So at the point at which this particular line intersects the x axis is nothing but the point x I plus 1 comma 0. So we substitute that in this particular equation, okay, and we will get minus f of xi equal to f dash of xi multiplied by x I plus 1 minus xi, okay. So we can divide throughout by f dash of xi, okay, and take xi on to the other side, and the resulting equation that we will get is xi plus 1 is going to be equal to xi minus f of xi divided by f dash of xi. Okay. So this is how we are going to use Newton-Raphson's method to come up with the next solution xi plus 1. Okay. So let us go to the algorithm that we developed for the fixed point iteration. We start with a single initial guess xi. In fixed point iteration, what we did was we assigned g of xi to xi plus 1. We are not going to do that in Newton-Raphson's. Instead, what we are going to do in Newton-Raphson's method is we are going to use this particular equation and assign it to xi plus 1. So our xi plus 1 is going to be nothing but xi minus f of xi divided by f dash computed at xi. Verify if xi plus 1 minus xi is less than epsilon. If it is less than epsilon, it is the solution. If it is not less than epsilon, we will repeat it until we get convergence. So this is going to be our algorithm for the Newton-Raphson's method. Okay, and the Newton-Raphson method, like the fixed point iteration method, will start with just one initial guess and not two initial guesses, and we will just increase the font size as before so that it becomes easy to view. Okay, so we wanted to solve this particular equation f of x equal to 0. So we will write this is our f of x, and let us differentiate f of x and write this as f dash of x is going to be equal to, so f dash of x is going to f dash of ln of x is going to be 1 divided by x minus 1. Just make this times New Roman. Okay. So now for Newton-Raphson's method, we need f of x, we need f dash of x, and that's essentially what will be sufficient for us to start with our Newton-Raphson's method. And I will just write down Newton-Raphson W. Okay. So iteration we have as before, we will have xi, fi and f dash I. We will have x of I, f of I and f dash of I. Okay, this is what we get. The iteration index will start with 1 and xi as before will start with 4, and f of I is nothing but 2 minus xi plus ln of xi. Okay, and f dash is nothing but 1 divided by xi minus 1. Okay, so this is our fi, this is our f dash of I. In the second iteration, our x of I plus 1, I will just write that down over here, that equation down, which we had just computed on the board. It is xi minus f of I divided by f dash of I. Okay, again the Newton-Raphson is also fairly simple to implement in a relatively simple one dimensional problem like this. So, x of I is nothing, x of I plus 1 is nothing but x of I minus f of I divided by f dash of I, okay. And so this is going to be our new solution, x of I plus 1, we will just drag this and we will drag this also in order to get f I and f dash of I, and then we will compute the error as well, and error is nothing but the absolute value of the difference, okay. So this is the error, and now we are ready as before, we are now ready to just drag and drop that particular row. We will just take this and maybe we will drag it say for 10 iterations and see where we go, okay. And we really did not need all these 10 iterations, we have reached our desired solution in essentially in just 4 iterations over here, okay. Alright, so we started off with x of I equal to 4, f of x of I we computed, f dash of x of I we computed, x of I plus 1 was equal to x of I minus f of I divided by f dash of I. This is how x of I plus 1 was computed. Again for x of I plus 1 we computed f, again we computed f dash, and from this again we kept computing x of I plus 1 each and every time for at each iteration, and we find that the solution converges, reaches the desired tolerance value of 10 to the power minus 4 in 4 iterations only, okay. So what we can now do is just compare, go back and compare the number of iterations that various methods have taken. This particular problem I spent some time in order to select a problem which showed the kind of features that are expected from these numerical techniques. This problem shows those features. So bisection method, it took 15 iterations to get to the solution. Regular-Falsy and the secant method took 5 and 6 iterations respectively. The number of iterations required by Regular-Falsy and secant methods are usually approximately the same as each other, because the underlying method of solving the particular problem to get xi plus 1 is not very different between Regular-Falsy and secant method. Fixed point iteration again took about 10 iterations or 8 iterations in order to converge, whereas Newton-Raphson's took actually just 4 iterations to converge. In general, the speed of iteration, which we will cover in our next lecture, goes Newton-Raphson's is faster than secant or fixed point, which in turn is faster secant or Regular-Falsy, which in turn is better than fixed point, which is approximately equal to bisection. We will cover this aspect later on in our lectures, that this is what the speed of iteration follows. Newton-Raphson's is better than the secant method, which is better than the fixed point iteration method in the the various open methods, okay. So this is essentially what we intend to cover using Excel. What we will do in the next lecture is cover some of the other aspects of so this is what we have done using Excel. We have covered bisection, Regular-Falsy, secant method, fixed point iteration method, and the Newton-Raphson's method using Excel. The way we have tried to use Excel is to bring out some of the salient features of each of these methods that are going to be of interest to us in discussing these methods going forward. We will talk in the next lecture about what we mean by the speed of convergence, how the convergence happens for 3 of these methods. We will take up bisection method, the bisection method, the fixed point iteration method, and the Newton-Raphson method, and try to analyze these 3 methods in the next lecture. What we have covered so far in our lectures is the single variable case of solving f of x equal to 0 using these 5 different methods.